Let's start at the beginning. 1, 2, 3. These are the first numbers that most of us learn, but it's important for us to really understand what these are. 1, 2, and 3 are answers to the question, how many? They are words and symbols that represent a number of discrete items. And while this observation is simple, it's also critically important to our understanding of numbers. There are actually two separate frameworks of the numbers we use. The mathematical terms are discrete and continuous, but this can also be understood as the difference between how many and how much. Have you ever thought about the difference between these questions? It is natural for us to ask, how many shapes are there? But it feels wrong to say, how much shapes? And we can ask how much water is in a cup, but we wouldn't ask how many water is in the cup. Your brain is intuitively swapping between two different frameworks of numbers. When thinking about the number of shapes, you would count each shape as a separate or discrete object, even though they may be different from each other, and we don't even care about the size of the object. The base quantity is one object, which we treat as indivisible. Quantities of water, on the other hand, are viewed as being continuous. We can increase or decrease the amount of water by very, very small quantities, rather than being limited to increases and decreases by some fixed unit. Enumeration is the process of answering the question of how many, and quantification is the process of answering the question of how much. These two ideas overlap in important and useful ways, but our focus here will be on enumeration. Let's go back to 1, 2, 3. We said that these are the answers to the question, how many? So if we look at the picture and ask, how many shapes are there? Our answer would be 2. It is important that we distinguish between the number 2 and the symbol 2. The number 2 is the number of shapes in the picture. The symbol 2 is just one of the ways that we can represent this in writing. Alternatively, we could use the word two instead of the symbol. Or we could give the answer in Spanish and say dos. We could just as well have used two tally marks. All of these words and symbols mean the same thing, which is the number that is this many. What we call it is not the important thing. What's important is that all of these refer to the same underlying quantity. A representation of a number is simply something that expresses the quantity in writing, whether it's words, symbols, or images. In fact, these two dots are also a representation. What we find is that it's impossible to write the actual quantity. We can only write representations of it. And this hints at a strangely deep question. What exactly is a number? It's not a tangible object that we can pick up and show someone. It's some sort of abstraction from a certain type of pattern. So are numbers real objects or just concepts? There are two basic camps in the philosophy of mathematics for answering this question: Platonism and nominalism. Platonism says that numbers are really real. Numbers are eternal, abstract objects that would exist even if we weren't here to think about them. 1 + 1 = 2 is a universal truth. And when we look at mathematics and see how it transcends time and culture, there's a sense in which this seems right. Nominalism says the opposite. Numbers aren't really real. They're just words or ideas in our heads and not a part of reality. Would it be true that 1 + 1 = 2 if no one is around to interpret the meaning of these symbols? And why introduce this abstract reality if it's not needed and doesn't really do anything? And there are ways that this also seems right. Which of these is true? I don't know. And I don't even know how I would convince myself one way or the other. Fortunately, when it comes to doing mathematics, it doesn't matter what you believe. But it is important to recognize that there are really deep and interesting questions about mathematics, even at this most basic level. How many dots is this? This isn't a trick question. There are 3 dots. But how did you determine that there were 3 dots? Did you actually count them out, 1, 2, 3? Or did your brain just jump to the number 3? Here's another one. If you've ever played games with dice, you probably instantly recognize this as 6, and you didn't count out 1, 2, 3, 4, 5, 6. There's a mental process called subitization, where our brains can determine the number of objects in a collection without needing to count them. Technically, this is known as perceptual subitization. Your brain perceives how many there are without engaging in a mathematical process like counting. A more advanced type of subitization is conceptual subitization. This is where you determine how many there are by combining perceptual subitization with a mathematical process. Here's an example. How many dots are there? Of course, the answer is 9, but the answer isn't the important thing. We are interested in the process. There are many different ways to see the answer. The straightforward dice interpretation sees this as 4 dots plus 5 dots, which gives us a total of 9 dots. However, different people might see different patterns, and so they might think about it differently. For example, this might be seen as a rectangle of 6 dots plus a triangle of 3, resulting in 6 plus 3 equals 9. Another way of seeing this is as 2 separate rows of 4 dots and 1 extra thrown in, which results in 4 plus 4 plus 1 equals 9. All of these methods give the same answer, and it's not at all clear that one is better or worse than another. The ability to conceptualize the same thing in multiple ways is an important and underemphasized mathematical skill, especially with younger students. Rather than encouraging them to do mathematical explorations, such as trying to see these dots in different patterns, they are often pushed towards brute force memorization and rote processes, and this runs the risk of depriving children of their innate mathematical curiosity, which harms their long-term mathematical development. Subitization is a mental process where our brains can determine the number of objects in a collection without needing to count them. There is a limit to what we can do with subitization. Perceptual subitization typically maxes out at around 5 objects, though we may be able to recognize specific patterns that involve more. And conceptual subitization is usually limited to combining just a few groups before it gets to be too much. When we reach the upper limit of our natural intuition, we see the need to develop more systematic approaches to help us go further. We can actually see the historical need for this in the language we use for numbers. The numbers 1 through 12 are very irregular in the sense that there is no logic to the names. It's just a memorized list in a specific order. Why is 4 after 5 and before 6? That's just the way it is. But once we get to 13, we can see a pattern begin to emerge. The numbers from 13 through 19 reflect the numbers 3 through 9, except with teen thrown in at the end, plus a little bit of linguistic mangling for 3 and 5. There's something that happened with how we started organizing numbers, and the evidence is in the language. Incidentally, you can also see the sort of thing happen in different languages, which reflects the different histories of different people. If you know French, you might know that the number 80 is literally translated as 420 or 420s, and this is the result of regional connection to the number 20. Let's imagine that we have a large number of objects. How might we determine how many there are? We could count the dots one at a time, but that would take a while, and it's easy to miscount somewhere along the way and not realize it. We can try conceptual subitization and let our brains cluster the objects based on patterns that it sees. This works for up to around 15 to 20, but then it becomes too much to track mentally, and it is also a very error-prone method. What we need to do is develop a systematic way of organizing the dots so that they are easier to count. And the first step of that organization is to create clusters of the same size. We're going to make clusters of 10, but we'll see later that there's nothing special about the number 10. As we count each cluster of 10, we're going to make vertical stacks with them to indicate that those dots have already been counted. Then we'll start over and count another group of 10, and another, and so on. When we don't have enough dots to complete another grouping, we can put the extras off to the side. And now we can see that we have 5 groups of 10 and 3 individuals. Understanding this is the first step of understanding how we organize numbers. What if we have a really large number of dots? We can execute the first step of this scheme, but what we would find is that we have a very large number of clusters of 10. So to keep with our pattern, we're going to cluster 10 groups of 10 together to give us another layer of organization. These clusters will have 100 dots in them. Just as with the individuals, we need to do this until there aren't enough to fill another cluster, and then set the extras aside. And we also need to remember that we had the original set of extra individuals. When everything has been regrouped, we can see that there are 4 groups of 100, 6 groups of 10, and 8 individuals. Let's think about what we've done. We started with individuals and made groups of 10. Then we had 10 groups of 10 to make 100. And if we needed to, we could take 10 hundreds to make 1,000. We can always take the largest group that we have and make a group of 10 of those to get another layer in this tower. And we can keep on doing this for as long as we need to. In this way, this process allows us to take any number of objects and put them into meaningful groupings. An important feature of this method is that we are able to reach arbitrarily large numbers without ever needing to count past the number 10. In the first step, we only needed to count to 10 dots. In the second step, we only needed to count 10 groups of 10, and 10 groups of 100, and 10 groups of 1,000, and so on. It's hard to overstate how big of an intellectual leap this is. We can now count as high as we want without ever needing to count past 10. After taking all of this time to organize the dots, it would be good to be able to write down the result in some useful way, saying things like 5 groups of 10 and 3 individuals, or 4 groups of 100, 6 groups of 10, and 8 individuals is perfectly meaningful, but it's also not very compact or efficient. A notational scheme that captures this information is known as the base 10 representation of numbers, also called decimal representation. That's just the way we normally write numbers. This is a situation where familiarity can breed contempt. Because this is the way you've interacted with numbers your whole life, it might be hard to step back and appreciate how efficient and powerful of a notation it is. But I hope you'll stick around and think through this because we do have a generalization coming. Let's look at 5 groups of 10 and 3 individuals. Let's get rid of the words and just focus on the digits. If we slide them next to each other, we get a place value system because the location of the digits, or its place in the number, gives us information about the value it's conveying. The 5 represents the number of groups of 10, and the 3 represents the number of individuals. We can do the same thing with 4 groups of 100, 6 groups of 10, and 8 individuals. We drop all the words and then slide the digits next to each other. It is important that the group sizes go from largest to smallest when moving left to right. This convention allows everyone to agree on the meaning of the locations of the digits. Let's break down this notation again. The rightmost digit represents the number of individual pieces. This is more commonly called the ones digit. The digit to the left represents the number of groups of 10, which is called the tens digit. Then come 10 groups of 10, more commonly known as hundreds. Each additional digit to the left would represent another 10 groups of the previous group. So next would be the thousands digit, then the 10,000s digit, and so forth. Each digit represents a number of groups of a certain size in the collection. In order to make place values work, we need to introduce the 0 symbol. We use a 0 when there are no groups of a particular size. The 0 here is essential to the place value system because we need a placeholder to enforce the location of the digits. If we have 2 hundreds and 6 individuals, we still need to have the 2 be the third digit from the right. And so we use the 0 to occupy the space and signal that there are no groups of 10. The history of the number 0 is quite fascinating. When we think about numbers as representing quantities, 0 serves as kind of an anti-quantity, where we are indicating the absence of objects rather than their presence. But we'll have to set that one aside for now. At the beginning of this discussion, we started off by creating groups of 10. It turns out there's nothing special about the number 10. We could have made groups of 2, 7, 16, or 43. The process of organizing would still be the same. We just make groups of a certain size, and then group those groupings, and group those, and so on until we run out of things to group. The general system for this is known as base n representation, where n is the size of the groupings we're going to make. We need to have a total of n symbols to represent the quantities from 0 to n minus 1, and these are called digits. In base 10, the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. For bases smaller than 10, we can continue to use these symbols, and for larger bases, we typically use letters to represent the digits after 9. So after 9 comes A, then B, then C, and so on. There's no standard for what you use after the alphabet, so if you wanted to play around in bases larger than 37, feel free to make up whatever symbols you want to use for those digits. Here is a concrete example. Let's say we wanted to express the quantity 123 in base 7. What would we do? Conceptually, we're starting off with a collection of objects and rearranging them so that they're organized around groups of 7. Remember that 123 means 1 group of 100, 2 groups of 10, and 3 individuals. We want to reorganize these dots so that we have groups built around the number 7 instead of the number 10. The first thing we're going to do is create as many groups of 7 as we can. When we do this, we get a lot of groups of 7, with 4 individuals left over. Since we have so many groups of 7, we're going to go up to the next level of grouping and make groups of 7 groups of 7. We see that we can do this twice with 3 groups of 7 left over. And now each collection has fewer than 7 objects in it, so we can write down the representation. There are 2 groups of 7 sevens, 3 groups of 7, and 4 individuals. In order to indicate that this is base 7 and not base 10, we can write a subscript 7 after the number. Technically, we could do this for the base 10 representation as well to be completely explicit in the notation. However, in the absence of notation that indicates the base, we typically assume that numbers are presented in base 10. Non-decimal place value systems are not a modern invention. The ancient Babylonians had a base 60 number system that used wedge-shaped marks as digits. This is known as sexagesimal. At first, it may seem strange, but artifacts of that base 60 system still exist in our world. there's 60 seconds in a minute and 60 minutes in an hour, so we think about time in a partially sexagesimal system. We like base n representations in mathematics because they are systematic, but it's worth noting that there are other representations of numbers that we use that are not systematic. It turns out that we can make the group sizes whatever we want them to be at every stage, and as long as those sizes are known, the quantities can be reasonably expressed and understood. The primary example of this is the system of coins. In the US, we have pennies, nickels, dimes, and quarters, giving us a representation built around the numbers 1, 5, 10, and 25. A given amount of money might be represented in multiple ways. For example, 53 cents could be 2 quarters and 3 pennies, or it could be 1 quarter, 1 dime, 3 nickels, and 3 pennies. Both collections of coins have the same value, even though the specific collections of coins are different. This simple idea opens the door to a very interesting problem in mathematics, known as the Frobenius coin problem. Given a collection of coins of different denominations, find the largest value that cannot be represented by these coins if such a value even exists. For example, if we had just a 2-cent coin and a 5-cent coin, the largest amount of money we cannot represent is 3 cents. In general, we aren't limited to having just 2 denominations of coins. The same question can be posed with any number of coins in any denominations. This problem also goes by other names. It's sometimes called the postage stamp problem, and sometimes called the Chicken McNugget problem. This is an example of how one mathematical concept can have multiple applications and interpretations. All we are doing is replacing the coins with stamps or packages of McNuggets. This turns out to be a very complex problem in general. The answer is known when there are only 2 denominations involved, but with 3 denominations there is no known general formula. It's a reminder of things that are often lost in a standard math education, which are things like curiosity and exploration. You can describe this problem to a curious second grader, and they can spend a lot of time playing around with it without realizing that they are on the threshold of some deep unsolved mathematics. If you have a little bit of programming knowledge, you can think about how you might programmatically search for answers, which you can use to generate data to search for patterns. That data might lead to identifying special cases and finding partial solutions to the larger problem. To close, I want to challenge you to solve the following sub-problem of the Frobenius coin problem. Suppose you have 2 denominations of coins. Can you come up with a method to determine when there is no largest value that cannot be represented by these 2 coins? To give you a little nudge, let's say that the coins are 2 cents and 4 cents. Can you explain why you cannot make any odd numbers? And from here, just see what ideas you have and see where they go. Maybe try both odd, maybe one even and one odd. Or maybe you just need a different concept to pull it all together. Just try it and see what happens, and please don't just Google the answer. Good luck. We're going to shift gears and talk about a completely different way of representing numbers. So far, our representations have been focused on making different types of groupings of objects. It turns out that there's also a geometric way of representing numbers. This geometric concept of number was the way the Greeks conceived of numbers. And there are a number of consequences of thinking this way. Thinking about numbers geometrically helps to develop a general understanding of numbers and numerical relationships that builds on some of our core intuitions. But these ideas aren't as helpful for actually performing calculations. One of the big challenges of math education is that some people want to reduce mathematics to just calculations. Here's a table to memorize, here's a computational algorithm, here's a formula, and so forth. But this limited view of mathematics is quite detrimental. Much of the innate curiosity that children have about mathematics is lost because they are forced to memorize and blindly follow a sequence of steps over and over again. I want to avoid that trap. Taking the time to explore numbers geometrically creates opportunities for insights that cannot be developed by performing calculations, and brings us to a much deeper sense of what mathematics is like. So let's dive into this conceptually rich perspective. The starting point of our geometric journey is the concept of a unit length. Draw a line segment. The length of this segment will represent the quantity 1. How long should it be? It doesn't actually matter. The system of numbers is built on relationships and not absolute quantities. If 2 people pick 2 different lengths as the unit length, it turns out that the geometric constructions that they would make would still contain the exact same information. One is just a scaled version of the other. In other words, one unit length is just as good as any other. This idea of a geometric construction can be formalized very carefully, but that will have to wait for another video. Intuitively, we think of these constructions as pictures that we can draw using just straight lines and circles. At this point, we're also imagining an idealized world where our lines are perfectly straight and our circles are perfectly round. In practice, we can only get approximations to this, but that's okay. The point isn't the drawing itself, but understanding what the drawing represents. Let's take a collection of objects. We want to represent this number as a length, but what length are we going to use for this? We can imagine associating each object with a unit length line segment. Then the collection of objects will be the length of the line segments when combined together into a straight line. If we do this, then smaller numbers will have a smaller total length, and larger numbers will have a larger total length. And if two numbers are the same size, then the line segments will have the exact same total length. Enumeration is the process of answering the question of how many objects are in a collection. This process lets us do enumeration without having to count anything. We don't need any digits or any other symbols. It's all geometry. All we are doing is associating each object with a length, rearranging them, and putting all the lengths together. The idea that we can figure out how many objects there are without counting is even more powerful than you realize. Using lengths to represent numbers gives us access to an important idea in mathematics known as the number line. We're actually only going to be able to get half of it for reasons that will soon be explained. We'll start by picking a point somewhere and calling it 0. Then we'll draw a line through that point. For convenience, we'll draw the line horizontally, but technically it could be in any direction we wanted. Then we'll arrange the line segments representing the numbers, starting from the smallest, so that the left sides line up with 0. Then we'll take each of those lengths and mark them off on the line. We can imagine doing this for a very long time and getting a very long list of numbers. What we end up with is something like a ruler. This ruler is the positive half of the number line. There's more stuff off to the left, but we'll have to wait until later to talk about that. Unfortunately, thinking about numbers as lengths does not give us access to negative numbers. Rulers are used to measure things, and in this case, the ruler helps us to measure numbers. There are two ways this can work. If someone gives us a collection of objects, we just place one object in each gap, and the number after the last object tells us how many objects there are. Alternatively, if someone gives us a line segment, we can line up one side with 0 and see where the other side is, and that tells us what number the line segment represents. But this second idea opens up new questions. What happens if someone gives us a line segment whose length is in between the markings? What sorts of numbers are these? The answer to that question is weirdly complicated in ways that will have to be its own video. But intuitively, there are numbers there. We just don't know what they are. And now that we've created this geometric perspective of numbers, what can it do for us? Let's take a look. We'll start by thinking about addition within this framework. Here are two numbers. Adding them together means that you just put these two lengths end to end and get the total length. At first, this seems a bit trivial, but it turns out that we can explain a lot of basic algebra with just this idea. To see how this works, let's think about the perimeter of a rectangle. Remember that the perimeter of a shape is the distance going around it, and that the opposite sides of rectangles are the same length. We will label them L and W. If we were to just naively measure the perimeter by tracing the shape, the formula for this perimeter would be L plus W plus L plus W. But we could also be a little bit more organized about this and put the L pieces and the W pieces together. Then we could express the perimeter as being 2L plus 2W. Alternatively, we could see this perimeter as being two identical capital L-shaped pieces. Since the total length of each capital L is L plus W, and we have two of them, the perimeter is 2 times L plus W. It's obvious that all of these represent the same total length, because they're all built from the same collection of line segments. But now imagine that we have these expressions without pictures. In order to understand what they mean, and why they are the same quantity, we would first have to explain the notation of algebra, develop the system of algebraic rules like combining like terms and the distributive property of multiplication over addition, and explain how to use these rules to manipulate the expressions to get them into those specific forms. The geometric way of thinking about it is something that early elementary students can understand, but the formal algebraic way isn't something that students are really ready for until late middle school or early high school. In fact, this geometric way of thinking can be seen as a stepping stone on the way to developing a deeper understanding of algebraic reasoning. But that's something else we'll have to come back to later. Subtraction can be represented as how much longer one number is compared to another. The question we're asking is, what's the difference in their lengths? And this is why we often call the result of a subtraction problem a difference. The way we can get it is to line up both segments on one side and see how far the longer one sticks past the shorter one. This is an unordered calculation in the sense that I can ask you for the difference between A and B, or the difference between B and A, and you will still give me the same answer both times. However, you might remember that a minus b and b minus a aren't the same value. So what's happening here? This is a place where we can see how the model we use shapes the mathematics we can discover. Implicitly, this geometric framework forces the result of subtraction to be a positive result, or possibly 0 if the two segments are the same length. Negative numbers simply do not exist in a geometric framework. And this points to one of the limitations of thinking this way about numbers. It doesn't make it right or wrong to think about numbers like this. There's value to having different models of numbers so you can apply the ideas in a variety of situations. You just need to understand the limitations of your models and their strengths and weaknesses. We'll finish things off with a puzzle to think about. Let's say you have two lengths. Is there always a length that evenly divides both of them? For example, if we have these two lengths, we could try to divide the shorter into the longer, but it won't come out evenly. We can try cutting the shorter one into two pieces and see if that works. In this case, it doesn't. Maybe 3? When we get to 4, we see that it finally works. But will this work for every pair of lengths? A lot of people's intuition leads them to think the answer is yes. You may have to cut them into very, very tiny pieces, but it seems like you ought to be able to do it if you try hard enough. When you can do it, the brute force method will eventually get you there. But the Greek mathematician Euclid had a much more efficient way of doing it. Here's his approach. He would first try to divide the smaller into the larger. If it divides evenly, then you're already done. But let's say that it doesn't divide evenly. We're going to take the last leftover piece and repeat the process with that piece and the shorter piece. And we will check to see if this divides evenly. If it doesn't, we take the leftover piece and repeat the process. And the process will stop when the remainder piece evenly divides the previous shortest piece. When this happens, the final remainder will evenly divide the two original lengths. We can see this by working our way back up from the bottom. The final remainder evenly divided the previous one because the process stopped. The one before that is a combination of the previous two, which means that it must be evenly divisible by the final remainder. And we can keep building our way back up to the start. At each step, we can see that the next line segment is built from the previous ones, and so must be evenly divisible by the final remainder. This method is known as the Euclidean algorithm, and has all sorts of applications in mathematics. But all of this hinges on the assumption that you can actually reach the bottom, and it's not obvious whether or not this happens, and under which conditions it would. And I'll just leave that as something for you to think about.